We're good, we're set up.
I'm here to supervise. It's really weird standing up.
Alright, this is the first time we've done this. Ms. Butler and I talked. Hey, your attention please. For many of you that want to go on to higher education, or you get into athletics, or you go into the military or some type of workforce, quite often there is a large gathering for instructional purposes. And those that have some aspirations, especially to go to a large university, your first couple of years you probably go to class with how many kids, Ms. Butler? 600 students in one lecture hall. And, you know, again, there's a certain decorum. You know, if you have a question, raise your hand. I don't know if I can see you or not. But so we're trying to give you the experience of a large group. I will call it a lecture for lack of a better term here. And so we expect your cooperation. And I'm sure we've done enough time. I could probably go on for 2 hours, but we won't. And, so we'll get going. So on your notebook, Cornell note style, and you can label this one EM Spectrum. And are you ready, Andrew? All right.
Doesn't even trust me. Don't look at him over there.
With the force. I don't like that word. What does it mean to be enlightened? Not necessarily. What does it mean to be enlightened? Yeah, to learn. Yeah, to become knowledgeable or something. That's what it means. Oh, I gotta get my speaker. Yeah, I will use a microphone. Now I will see if I can use the force to change the screen. Why is it not going? Yeah, I don't have my lightsaber on.
There's too much electromagnetic force going on here.
Ah, there the force is working now. Okay. You probably heard me, especially in my class, you know, Einstein's lab. Well, you know, there's a great quote by Albert Einstein here. It says, once you stop learning, you start dying. No matter what age you guys are, whether you're old like Mr. Peckus or Mr. Goff, we're always learning. We're always learning. And so as we go through this lecture today, keep that in the back of your mind. You know, not everybody's got the same interest in everything, and that's fine. Always learning as we go through things. So, first thing we need to talk about, we talk about the electromagnetic spectrum, is what is a wave. Anybody want to, how about, anybody up there want to tell me, what's a wave? Yeah, okay, we can read it, true. Okay, it can be up and down, all right. What does a wave really do, though? What is its major function? Travel. Transports energy without taking matter with it or moving the matter along with it. So when you think of a wave, it transports energy. This could be a sound wave, it could be a light wave. We're looking at the electromagnetic spectrum. It could be a water wave. if you paid any attention over the weekend, I think it was Storm Jonas on the East Coast. The East Coast, especially along the coastline, all the waterways had so much force with them, there was a lot of erosion going on. And now I think they're trying to bring the federal government to maybe curb the erosion or see what can be done there. So waves really carry energy. And the medium, which is a fancy term for the matter, or the stuff that it goes through, does not go along with it. You know, you think of a water wave breaking on the shore of Grand Haven or Holland, all the water just doesn't pile up from across the lake. And the water flows back, and actually the energy of the wave goes through the water on an up and down movement. And so as you stand in the water, you can feel that energy with a water wave especially. The word spectrum. Yeah, spectrum health. What does spectrum mean? You know, we talk about the electromagnetic spectrum. What does the term spectrum mean?
Wide scale.
Wide scale, very good. From what, beginning to? Yeah, from a beginning to an end. You think of spectrum health, they'll bring you into this world. They'll take care of you throughout the course of your whole lifetime. And, well, once you pass away, you pass away, but they will cover you for everything across a broad spectrum or a broad range of medical facility. And it's always interesting when you look at, I was looking at the Spectrum Health logo, and you can see there's a change in color there. Now granted, the blue and the green are there, but it also very much similar to the electromagnetic spectrum, the visible light spectrum. There's a reason they pick out the term spectrum for spectrum health. They cover a wide range of medical facilities, medical procedures, and so forth. All right, so what is the EM spectrum? Yeah, so we're looking at this. You got a copy of this, maybe you all got a copy of this in your class. You know, we talk about a light wave, but the light wave is a part of the electromagnetic spectrum. It is a very, very, very tiny part of the electromagnetic spectrum. As you can see from the diagram up here, hopefully not with my laser. So as you can see, the light is just a small part here. It goes all the way from radio waves, television, microwaves, infrared, get into visible light, X-rays, and then cosmic rays, and so forth. Do you have electromagnetic rays going through you right now? Yeah. What type? Do you think it's gamma radiation? No. Why? Raise your hand, so pick. What type of waves do you think is coming through? Let me ask you this. Think about this. If you're going to say ultraviolet, can light pass through your body? No. So now we're looking at something TV or maybe radio. You constantly have waves going through you. Radio waves are going through you. All the waves to the left side of this. You guys all use a cell phone.
Yeah.
Well, though that signal gets there through a wave. So waves are constantly going through you right now. They don't cause you any harm at that frequency or wavelength. As you move up the scale, your eye is very sensitive to the visible light range. And as you go through the scale, you get to ultraviolet, which we may have talked about. Ultraviolet radiation can cause what? Cancer. Yeah, sunburn, cancer. So that's destructive. If you go up to, if you get a dental x-ray, what does the dental hygienist do? Put a lead jacket on you, and typically they go out of the room. So that tells you those are probably a little more intense and there's more energy there. And In fact, as you go to the right, you get into cosmic or gamma radiation. Those are very, very destructive. You're getting into what's happening in the sun with nuclear fusion. You're getting to the whole idea of atomic bombs and so forth. Yes?
Where do water waves come in the...
Okay, that's a water wave. A water wave is a wave, but it is a mechanical wave. These are electromagnetic waves, and they are produced by vibrations. So there's two more words you can put in your notes. Mechanical waves, in fact, you just got ahead of me a little bit. Mechanical waves are produced by vibrations, and they need something to go through. A mechanical wave is produced by vibrations, and they need something to go through. A water wave, a sound wave. Electromagnetic waves, on the other hand, can go through the vacuum of space. What is a vacuum? A vacuum is the absence of matter. Radiation. These are typically transmitted by radiation. The emptiness of space. The sun is 93 million miles away, give or take a little bit. We feel the energy from the sun because it's an electromagnetic wave and it can go through the emptiness of space or through a vacuum. Real important point up here. Look at the relationship between frequency and wavelength. What do you notice off this particular graph? Update. Yes. Very good.
Yeah.
As wavelength decreases, gentlemen, you're writing this down, right? As wavelength decreases, or the wavelength gets shorter, frequency does what? It goes up or increases. As wavelength decreases, frequency increases, and energy increases. That's the key relationship in the electromagnetic spectrum. As wavelength increases, frequency will decrease, and energy will also decrease. That relationship does show up several times in the future here. Hint, hint, hint. So the higher the frequency, the shorter the wavelength, the more energy. Graphically, when you look at that particular graphic up there, you can see, when you get down the radio wave section, you can see they're longer. You get up by the gamma radiation, the cosmic rays, they are very, very short. Short waves, high frequency, high energy. Notice when you get into the visible spectrum, I think you guys all had middle school Roy G. Biv, right? So if you look at that, what is the low frequency end of the visible light spectrum? Red. The low frequency side is red. The high frequency side is violet or purple. So when you write down Roy G. Biv for the spectrum, it's going from low frequency, longer wavelength, all the way up to higher frequency, shorter wavelength. The whole idea of Roy G. Biv, and it goes in that particular order there. Wavelength is measured in meters. Standard unit of measurement in the metric system is the meter. And so you're going to see 10 to the minus 8, 10 to the 10th meters, very small numbers and very large numbers. Frequencies measured in hertz. And we'll get to that in just a second. Just like the rental car HZ, not named after a rental car company, but it's the same thing. So know that relationship. As frequency increases, wavelength's got to decrease, energy will increase. Yes? Hertz, H-E-R-T-Z. We'll have another slide with it in just a second. Just like the rental car. Electromagnetic spectrum. As the name suggests, part of it is going to be electric, an electric field. Part of it's going to be a what? A magnetic field. So you've got two things going on with an electromagnetic spectrum. And we're not going to get into the fields a ton, you'll say that for physics class. But Kadarius, make sure you remember this, that there's an electric field and there is a magnetic field involved. Both those fields are perpendicular to each other. You probably played, I don't know, probably in middle school, you had magnetism. You put a current, a wire across a compass. What happened to the needle? It spun around. An electric field can influence a magnetic field, and a magnetic field can influence an electric field. Back in the day of the old CRTs, cathode ray tubes and computer screens, if you put a magnet on the screen, you can actually mess up the colors and so forth, because a magnetic field can influence an electric field. And those two fields are perpendicular to each other. Those two fields are perpendicular to the direction of motion. The direction of motion, you better write this down. And we'll probably do the demo in class, Ms. Butler. Those three things are all perpendicular to each other. In other words, another term for perpendicular is what? At a what? 90 degree or at a right angle. Okay, very similar to the water wave, an EM wave is a transverse. An EM wave is a transverse wave. Ms. Butler, come down here real quick, and we can do this. Okay, this is the classic. Go ahead, stretch her out, stretch her out, stretch, and don't let go. Okay, so this is the classic transverse wave. Notice, the wave moves perpendicular to the direction of travel. In a transverse wave, the wave moves perpendicular to the direction of travel. The direction of travel is from me to Ms. Butler. The direction of the wave is up and down. Now, we could go this way with it. The direction of a wave is still perpendicular to the direction of travel. And we could even go at a 45. The direction of the wave is perpendicular to the direction of travel. That is a transverse wave. Electromagnetic waves are transverse. And probably demo this again in class with also. Thank you. Okay, wavelength. Very similar to a water wave, crest to crest, trough to trough, however you want to measure that. And again, wavelength is lambda, it's kind of an upside down V, if you will. EM waves travel at a constant rate through a vacuum. Electromagnetic waves through a vacuum are the fastest things going. And that is a lowercase c, or a speed of light. Stop throwing stuff. And that is 300,000 kilometers per second, or 3 times 10 to the 8th meters per second. You need to know that value. 300,000 kilometers per second, or 3 times 10 to the 8 meters per second. That is a constant value. That is the speed an EM wave travels through the vacuum of space. What's going to happen to an EM wave when it strikes an object or goes through water or the atmosphere? What's going to happen to the wave speed? It's going to slow down. Yeah, kind of common sense tells you if it's going as fast as it is through the vacuum or the emptiness of space, once it goes through something, it's going to slow down. So keep that in the back of your mind when you start thinking about the speed of an electromagnetic wave. But for all your calculations in here, dealing with electromagnetic waves, you're going to use C, that constant value. The other one, the time between passage. How long does it take one wave to get to a certain point? How long does it take another wave to get to that same point? You stand out in the water, Lake Michigan or some lake, you can sit there, you can measure, it takes 5 seconds for one wave between the both crests to get to me. So that's a period, 5 seconds. That's all you're talking about there. Frequency. Frequency, and it doesn't show up real well there, but that is a lowercase f. Frequency is a lowercase f. The number of crests that pass a point, and we're going to use per second. Frequency, the number of crests that pass a point per second. The higher the frequency, the more crests you got passing that point. The lower the frequency, the less wave crests that pass that point per second. That goes right back to that whole idea. If frequency is high, wavelength's got to be short. A good example of this, if I wanted to get you all out of here and I'd have you stand in a straight line, if we want to get you out of here in the least amount of time, what's going to be the distance between each individual? Yeah, it's going to be very, very small. So therefore the frequency goes up, wavelength goes down. If I end up putting 10 feet between you, if I end up putting 10 feet between you, the frequency is going to go down, but the wavelength goes up. Amplitude, this is a little different than a water wave. Water wave, we talked about height. And height was measured from where to water wave. Trough to crest or crest to trough. In an electromagnetic wave, the amplitude is measured from the line of equilibrium or the line of rest or something, a line that really divides the wave, the top and the bottom. And the amplitude is measured from that line to the crest or that line to the trough. That is the amplitude. So make sure you definitely got that into your notes also. People want to confuse an electromagnetic wave. We see the amplitude. They'll go through and measure from the trough to the crest, and that is incorrect for an electromagnetic wave. Amplitude, from the line of origin, the line of rest, the line of equilibrium, it's all, to the crest, that would be the amplitude, or it could be to the trough, that would also be the amplitude. Looks like I got somebody out there taking their notes on their phone. That's a really good idea. I like that. Probably texting all this information out. That's awesome. Okay, get a wavelength real quick. You can see crest to crest, trough to trough. Technically, you could use any 2 points on successive waves. Doesn't have to be the crest, doesn't have to be the trough. It could be any 2 points on successive waves, but crest to crest, trough to trough is easy to find, easy to measure. Some common units of wavelength. Now we said the standard unit of measurement in the metric system is the meter. But the most common unit in electromagnetic waves is called a nanometer. NM, and that is 10 to the minus 9th. 10 to the minus 9th meters. And that is a nanometer. So if you see that term, that means 10 to the minus 9. So if you see the wavelength is 100 nanometers, that's 100 times 10 to the minus 9. That's a very, very common unit when you start talking about wavelength. Another one you'll see, we won't use too much, is an angstrom, which is a capital A, and that's 10 to the minus 10 meters. Again, when you start talking wavelength, they can get really, 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 really short. On the other end, when you start talking about radio waves, they could be into the hundreds or thousands of meters. They can be very, 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 very long. But that's a real common unit when you start talking about the electromagnetic spectrum. And when we start calculating for our purposes, we'll do everything, probably everything in meters. If you can convert to nanometers, that's fine. Okay, frequency, lowercase f. Again, the number of waves that pass through a given point per second. So if I had 5 waves per second, the frequency would be 5. 5 divided by 1 is 5. If I had 10 waves per 2 seconds, what would the frequency be? 5. It's the number of waves that pass a given point per second. What? The number of waves that pass a given point per second. If I had 10 waves, and it takes those 10 waves to pass a given point in 2 seconds, what's the frequency? 5, because it is per second. It's very similar to density. Density is grams per 1 milliliter or grams per 1 cubic centimeter. Very, very similar to that. Sometimes you'll see a problem where you may get it where it says cycles per second. It's really the same thing. It's named after a German scientist, Heinrich Hertz, and hence the term named after him, Hz, frequency. When you guys probably don't look at radio dials anymore, but when you listen to your favorite station, whatever it happens to be, like 107.3, that's going to be kilohertz. That is the frequency. They are giving you the frequency. Real quickly, if you listen to FM, ladies and gentlemen, FM is frequency modulated. In other words, they change the frequency. If you listen to AM, AM radio is amplitude modulated. In other words, they change the amplitude of the wave. That's where the term FM and AM comes from. Okay, one other thing I want to touch on real quick, and those are my 2 buddies there, as you can well see. I always talk about light speed. Nothing is faster than the speed of light. Millennium Falcon, of course, there. Yeah, unfortunately, in the last episode.
I didn't watch you guys. Don't give it away.
Okay, the speed of light. Again, review this with you. This is important. You've got to get this information. It is a constant value. Don't be surprised if you get some problems on the assessment and you only get one number, because you already know the other number. When we are talking electromagnetic spectrum, the speed of light. For all us English speakers, it's about, talk about English units, feet, pounds, I don't know why, but we still use that quite a bit. It's 186,000 miles per second. The English units versus the metric units. What's the beauty of the metric unit? Anybody recall? Everything's based on the number 10. Very good. Very good. So if you go to English units, 186,000 miles per second. Pretty fast. Know that figure. That is a lowercase c. It is a constant. It is the speed of light. Oh, all right, go ahead. Speed of light. Are we good? All right, go ahead and put that down. Huh?
Thank you, Sean. Very nice.
All right, a couple more here. Guys, speed of light. C, 3 times 10 to the 8 meters per second. Through a vacuum. Okay, the formula. For anything less than an electromagnetic spectrum wave, such as any wave, the formula is Ws wave speed, or V for velocity, and we're not doing here right now, we're paying attention, this should all be going into your notes, and it is frequency times wavelength. The formula, frequency times wavelength, wave speed or velocity. If it is an electromagnetic wave going through the vacuum of space, you already know the wave speed. 3 times 10 to the 8th meters per second. If it's going through water or the atmosphere, it's going to be slower. You probably will have to be given that value. But, yes. That is, wave speed equals frequency times wavelength. So, wave speed is meters per second. Frequency is hertz, or the number of crests that pass a given point per second. And then when you talk about wavelength, it's going to be in meters. And so your units of wave speed, ladies and gentlemen, is meters per second. So there's I put an example up there. Just a typical example you would probably see. What is the speed of a wave that has a frequency of 5 hertz and a wavelength of 2 meters? Wave speed, frequency. So you have 5 over 1 second. Probably should have put a 1 there and I didn't. Times 2, 10 meters per second. That would be the wave speed. Very, very similar problem to density. You've got 3 variables. You've got to know how many. You got to have 2. Very, very similar problem. Okay, ladies and gentlemen, for an electromagnetic wave, C equals the speed of light in a vacuum, 3 times 10 to the 8th meters per second, and that is a constant value. So example is, what is the frequency of an EM wave that has a wavelength of 2 meters? You're not going to be given the speed of light. It is a constant. So we know it's 3 times 10 to the 8th meters per second equals frequency times the wavelength. So if you go ahead and do the math, you'll see that it'll come out to about 1.5 times 10 to the 8th hertz. The unit of frequency is a hertz. So the frequency units be measured in Hz. I believe on the worksheet there's a fair number of these problems on there, so you ought to get pretty good at those. Some things to consider, which we talked about a little bit of a review cap here. As frequency increases, the wavelength decreases. Know the converse. And we also know the higher the frequency, shorter the wavelength, higher the energy. That relationship is very, very important. The speed of light is also more famously known in this equation, E equals mc squared, where E is the amount of energy and m is the mass of the object. And that amount of energy is the speed of light squared. 3 times 10 to the 8, you square it, multiply by mass, that is a tremendous amount of energy. And of course that is Einstein's famous equation there. And I think everybody's probably seen this equation at one time or another. And I think I've got one more slide and we'll turn you loose. E equals mc squared. And as we talk about Yoda, really, you must unlearn what you have learned to gather new knowledge. So with that,